Hi, my name is Michael Lavara, and welcome back to my video series on paint and materials effects testing, part 6, where I look at the effects of 100 low lead and unleaded avgas on our aircraft and systems as fuels have been rolled out. In this video, I'll talk about the CEH lawsuit and the recent ruling back in May. I'll discuss an airport commission presentation where both George Brawley and myself were present to give our perspectives on experiences of users with G100UL. I'll update you on some affected aircraft that have now returned back to service, and I'll introduce a new aircraft, the Beech Baron 58, that's recently had issues. I'll dive deeper into O-rings and swelling testing and present the results of that. And I'm going to look at the materials compatibility topic in a broader scale, looking at some historical resources, and also diving into the Piston Aviation Fuels Initiative, i.e. the PAFI program, and how it differs from the STC pathway. And lastly, I'll close with the FAA's recent statement on grant assurances for federally obligated airports. So let's dive in.
To start, the Center for Environmental Health's lawsuit that essentially sought to ban the sale of 100 low lead in California was ruled upon back in May. And the judge took a deep look at this and came up with what I think is a reasonable ruling, basically stating this motion is premature and that there is no currently available high-octane unleaded avgas that is commercially available. In the order, the judge did deny all of CEH's motions, but he did leave the possibility for them to reopen this case as the fuel science evolves. On June 3rd, George Brawley and myself were asked to present to the Santa Clara County Airports Commission, which governs the Reed Hillview Airport. We both presented on our unique perspectives of G100UL and users' experiences in adopting this new unleaded fuel. The public was invited to speak, both in person and online, and several users of G100UL highlighted their negative experiences with the fuel. As you can see here on the Airports Commission agenda and docket, there are several presentations and many items submitted to the docket. I've linked this down below, where you can also find the audio recording of the evening's talks. One of the more notable presentations that followed the fuel discussion was done by Stephen McHenry and Doug Rice, which dug into the lead studies and blood lead levels of children around the airport and in the entire Bay Area. The presentation is very well put together and based on factual data. It's listed as item 6 in the Airport Commission meeting. The STC versus PAFI program is likely misunderstood, and a lot of individuals comment that the FAA has failed to find a solution for avgas, but likely misunderstand the two different pathways that exist for certification of a fuel. I think it's important to understand these differences between the pathways, and I'll set up a little bit of it here in the beginning of the video and then circle back at the end after I discuss some materials topics. There's a wealth of information on both the FAA site and the EAGLE, the Eliminate Aviation Gas-Leaded Emissions website, on this topic. One of the PAFI program updates in 2017 clearly laid out their mission, which is to evaluate candidate unleaded replacement fuels and identify those fuels best able to technically satisfy the needs of the existing aircraft fleet, while also considering the production, distribution, cost, availability, environmental, and health impacts of those fuels. At the Airport Commission meeting, I presented the first slide from the Lessons Learned document from the PAFI program, and it states that materials compatibility, engine durability, and commingling with 100 low lead were shown to be the critical criteria overshadowing detonation as a key differentiator of an unleaded fuel. I think that's an extremely important statement, especially given the experience of many users of G100UL at Reed Hillview and other local airports that have had adverse effects. Because detonation doesn't matter if your aircraft's grounded due to airworthiness issues, leaks, and seal problems. Building off the first lesson, the second lesson discusses test protocols and materials test advisory committees setting up best practices for materials compatibility testing of a new fuel. The past 6 months and series of videos have taught me that materials compatibility testing is more important than I ever thought. And to further emphasize this, it seems that GAMI is learning this lesson. If one were to purchase the STC today, there now is a disclaimer on the STC checkout page. And reading the wording in the disclaimer, it does seem to indicate that they're finally admitting some of the issues in the field may be related to usage of their fuel, and that the testing I've done to validate that is essentially valid. Let's take a look at how fuels are approved under the certification process. There are two distinct methods for the approval of a fuel. The first is the PAFI program through the Fleet Authorization pathway. The second is the STC pathway. And there's differences between the two. For the STC method, the applicant and the FAA agree upon a test plan between each other in order to certificate the fuel against Part 23 standards. In the Fleet Authorization pathway, the fuel applicant submits the fuel to the FAA's PAFI initiative for testing. It goes through a rigorous set of standardized tests for each fuel that's applied upon, and then the results are presented as pass or fail. This, I think, is where the difference is in the current fuels in the market. The STC method may not have as much rigor as the PAFI program on materials compatibility. And when I talk about rigor, I'm referring to the process by which a specification for a fuel is made. The STC pathway allows for an independent specification or an ASTM production specification. An independent spec may not have the rigor that consensus-based standards like an ASTM production spec has, where it is peer-reviewed by industry. And as I've alluded to before, the PAFI initiative has a very comprehensive materials compatibility test plan, one that every candidate fuel is tested against. And since GAMI has not revealed their materials compatibility test plan, it's unclear what actually they tested the fuel against. The DOT did put out a memo last November talking about how they're going to audit the STC process to ensure that it's universally applied across all certification offices. Later in the video, I'm going to dig more into the lessons learned that's been presented by the FAA's Piston Aviation Fuels Initiative. I think there's some important stuff in their documents. Let me pivot to some aircraft updates. I'll update you on the Cirrus that had major leaks on the wing, a PA-32 which has had leaks and now a fuel pump issue, and a Beech Baron 58 I've recently learned about in Mississippi. The Cirrus SR-22 that I reported on back in February has finally been repaired and is now back at its home base at Reed Hillview after being down for some 5+ months. The owner is excited and happy to have the aircraft back after this extended downtime, which included repairs to both wing tank sealant and multiple areas of paint on the aircraft, as you can see here. One of the aircraft I've reported on previously is a PA-32 at Reed Hillview. The aircraft ran about 40 hours of flight time on G100UL, utilizing 325 gallons of the fuel. The engine was overhauled in 2017 and has less than 400 hours since overhaul. There's been multiple trips to the maintenance shop, suspected fuel injector clogging, and essentially all the fuel sender gaskets have leaked, damaging paint on multiple areas of the wing. It's important to note that these fuel sender gaskets were installed new with avionics work done in 2021, so they're not that old. The other item to highlight is that after switching back to 100 low lead is when the latest fuel sender gasket leak occurred, along with the engine-driven fuel pump leaking and having to be replaced. I'm going to touch on this later in the video, but this aircraft highlights one of my theories about the removal of plasticizers in rubber compounds with G100UL and the ongoing materials compatibility topic. My understanding is that G100UL can be purchased from a total of 4 airports currently in the United States, 2 in California, 1 in Mississippi, and while not reported here, a smaller FBO in Texas. Thus, usage of the fuel has been limited, and the majority of issues have been reported in California, where likely the most fuel has been sold. I was recently made aware of an aircraft in Mississippi that had utilized G100UL. It's a Beech Baron 58 that experienced leaks and paint degradation after relatively short-term usage of the fuel. Running about 250 gallons of fuel between April 10th and May 24th, the aircraft went in the shop on May 24th because an older bladder was noted to be leaking. While in the shop, the recently installed bladder that was manufactured in late 2024 started leaking. The bladder material was reported to be compromised, along with the cork gasket being deteriorated. When fuel was drained from the new bladder, it had been reported to have a darker appearance consistent with the bladder color, black. And to revisit my earlier video where I looked at the AOPA Baron and the issues they noted there at AirVenture 2024, the damage on the BE-58 in Mississippi looks very similar, where the fuel followed the spar to the lowest point near the jack pad. Nonetheless, this adds another data point to Beech Barons using the fuel, and whether the AOPA Baron and this Baron in Mississippi have had the same issues will be told with time. The Baron fueled up at Tupelo, Mississippi, and the FBO currently has a notification out that G100UL is temporarily unavailable till further notice. Someone who inquired with the FBO noted they were told their fuel truck's out of service, and they're currently investigating why. Questions have been raised about the O-rings that I used in video number 5 with the Cessna 421 fuel selector. I want to highlight an important point in context. There is no parts catalog or IPC or manual available for this fuel selector. I measured the O-rings that came out of the fuel selector I acquired and compared best design practices from several O-ring handbooks on sizing, assuming proper material compatibility with fluid and swell less than 10% for a dynamic application. -014 O-rings best match the dimensions of the removed O-rings and shaft selector interface without introducing excessive stretch when installed, i.e. less than 5%. And I have initiated a longer-term test to look at the -013 O-rings in situ, but I don't have any results at this time to report. Let me share some of the preliminary data that I do have on what the O-rings do when exposed to different fuels. In the video that was posted of GAMI's O-ring testing by Scott Perdue of Flywire, O-rings were pre-swelled at elevated temperatures, and as best as I can tell, rammed into the fuel selector for testing and not performed in situ. So to clarify, all of my tests have been with fuel from the pump. Nothing is sauced or added to bring the fuel to some extreme data point or corner case. I started with unswelled O-rings that were subjected to fuel in situ, and the fuel selector was then exercised. O-rings were sourced from aviation sources. There was a suggestion that my immersion data was too short. I have previously had data on swelling over weeks, and I reran it for some tests in both heated and non-heated conditions. Much has been said about O-ring swelling in both ambient and heated temperatures, so I set out and ran some tests. The first was 100 low lead ambient soak, G100UL ambient soak, and G100UL heated to about 135 to 140 degrees F. And here's the results of those immersion tests over about a 2-week span. 100 low lead swelled to about 10% additional volume within the first day or two, and then relaxed to about 3 to 4% swell over time. The bottom plot is a combined ambient soak between 60 and 90 F, and a heated soak of G100UL immersed O-rings up to about 140 degrees F over 2 weeks. Out of this, they eventually settled to about the same swell level, gaining 40% additional volume over time. The only notable difference is that the ambient soak seemed to get to peak swell slightly faster than the heated soak. There's been some comments on the internet suggesting that calculating the volume change by percentage for an O-ring is an academic exercise. I actually disagree with that because, as noted here, the volume change means that there's a chemical reaction going on, and not all swell is good. This means that any deterioration of the mechanical properties of an O-ring will take time to fully materialize. A lot of questions about materials replacement and who can perform work have been raised, especially related to mechanic privileges. There is no publicly available manuals or illustrated parts catalog available for the 421's fuel selector. Can a mechanic legally field overhaul one? Can they replace the O-rings with, quote, modern materials? And really, where is the approved data and cross-references for those materials? And while GAMI's ICA mentions replacement of materials while performing maintenance where practical, I don't believe this statement is a blanket authorization to just go replace materials with your liking, especially without specific manufacturer or aftermarket FAA PMA approval for those components, with cross-references and specific designations. And since there's no manual or IPC for the 421 fuel selector, let's look at mechanic privileges. Under 14 CFR 6581, it says a certificated mechanic may not exercise the privileges of his certificate and rating unless he understands the current instructions of the manufacturer and the maintenance manuals for the specific operation concerned. Given that statement, I think it's clear that unless manuals and procedures were available for the fuel selector designed to the mechanic, that the unit is not field serviceable. In addition, there are things like pressure tests and breakout forces for actuation of the fuel selector that would need to be performed, and there's no manual for that. And if new materials were put in place, one would need to test the fuel selector across the wide temperature ranges that the aircraft like a 421 would be subjected to, from the hot Arizona sun on the ramp to colder temperatures at 30,000 feet. And lastly, any manufacturer or repair station would have to modify their processes and manuals in order to install modern materials. along with performing testing to ensure the new materials pose no hazard to operation. Undoubtedly, the discussion on any new fuel being introduced will raise material compatibility concerns. But if those materials need to be changed, there needs to be specific approvals and the ability for a mechanic to legally replace them. Much has been said about the aromatic content of fuels and how 100 low lead can have as much as 30% of aromatics by spec. The FAA did a nationwide sampling in 2014. This sampling showed the mean content observed at that time was around 7.25%, with samples up to about 17.7% noted. My understanding is that the 30% content, which has been touted, is an outlier and was found in a batch in the South. This fuel was dosed with higher aromatics in order to bring it up to spec and is not a regular occurrence. We also need to be cognizant of terms. Aromatic and aromatic amine are actually two different components of G100UL. While xylene in G100UL could be correlated with toluene, the M-toluidine in G100UL is different as an aromatic amine. And while I don't know the inner workings of the FAA, my understanding is that the STC process is totally separate from the Piston Aviation Fuels Initiative. I point this out because the PAFI program appears to have dealt with some pain points with different components of aviation gasolines, especially with aromatics, where here they point out that it affects elastomers to a greater extent than other components in gasoline, even pointing out that it can dissolve or cause severe swelling of rubber and rubber-like substances unless special mitigations are utilized. This publicly available article from Aviation Week ran after AirVenture in 2024, and some comments were noted in there from VP and Lyondell related to them saying they thought they'd be able to make a drop-in unleaded replacement, but they don't believe it's possible. And much of it points to materials compatibility as being one of the issues with fuels. The main challenge is replacing lead, which is essentially a metal element, with some form of chemical to get the octane booster. The article states that UL-100E had completed the first phase of ASTM D7826 materials compatibility testing, and that lack of information on materials testing of G100UL was a stumbling block at that time. Also quoted was that materials testing is critical because that's what may have caused many of the previous PAFI fuels to fail. Since ASTM D7826 was mentioned, let's have a quick look at that. It's the standard industry guide for evaluation of aviation gasolines. It includes material compatibility guidelines. And the main question with G100UL has been what tests and methods were performed on the fuel since they didn't get an ASTM specification. And even though they've gone down the STC route, Swift has still secured ASTM specifications for their fuel and performed laboratory testing of materials compatibility. Lastly, VP Lyondell is going through the PAFI route, and that requires securing an ASTM spec for UL-100E. Eagle's March 2025 update highlighted an important fact that an ASTM spec is found in just about every fuelable for purchase today, even outside of aviation. Fuel recipes for aviation have to balance many factors, but yet they all conform to ASTM D910 for leaded avgas. This includes octane, anti-knock additives, vapor pressure, boiling point, freezing point, cold starting requirements, distillation curves, and a lot more. And while fuel recipes have to balance all those other factors, the octane enhancement is a challenge for replacing 100 low lead. My understanding is octane boosters can be generalized into four categories: metals, aromatics, oxygenates, and aromatic amines. The removal of lead as an octane enhancer has provided a challenge for materials compatibility, and since lead typically does not affect rubber and elastomers like chemicals do, the replacement of lead with items like aromatics, oxygenates, or aromatic amines may introduce materials compatibility issues to varying extents. Let me expand on this now with what I've uncovered with some publicly available materials related to previous fuel candidates. My research over the last 6 months has dug into some of the previous PAFI fuels. There were 2 candidate fuels that went through the PAFI program up to about 2018 over a 4 to 5 year span. That included an offering by Swift and Shell. The FAA hasn't released any details on either of the fuel's compositions, but one can infer from patents and some online publications what the fuels were likely composed of. Then, a review of the PAFI lessons learned documents add additional clues. An update from the PAFI program in 2018 adds additional clues to digest related to the fuel compositions. A publicly available article in Aviation Consumer dug into Shell's Unleaded Avgas update a couple years ago, and it notes that they explained using aromatic compounds instead of lead as an octane enhancer. The article then goes on to compare Shell and GAMI's fuel development efforts, noting that both of them are using an aviation alkylate along with high aromatic content in order to boost the octane. On the other hand, Swift's fuel was noted to be a totally different composition and would be heavier by about a pound per gallon than Avgas. It's important for context to point out that both Shell and Swift did not continue with the PAFI program with the particular fuel compositions presented here. I was able to locate some patents related to Shell's fuel offerings for Avgas, and they talk about a high octane unleaded aviation fuel having high aromatics as noted here. In the patent, they actually talk about the difficulties in replacing lead and getting octane enhancement in an unleaded avgas. This includes not impacting the flight range, vapor pressure, temperature profile, and freeze points that meet the aircraft engine startup requirements and continuous operation at high altitude. Like most patents, they show various embodiments of their invention, including using toluene and other components to achieve this new aviation avgas. But what was most striking to me was their comment here about C8 aromatics, specifically pointing out that aromatics such as xylene may have materials compatibility issues, particularly in older aircraft. While it appears that Shell learned some lessons with xylene and opted to use toluene in their candidate fuel, let's look at GAMI's STS, which points out they have between 20 and 40% by volume xylene in their fuel. What does GAMI's new STC disclaimer say? It says the age increases the risk of fuel seepage and potential paint damage with G100UL, even if no issues are observed with 100 low lead. Sounds familiar. To me, it seems like there should be some limitations on materials in GAMI's ICA. Many of you might recall my reporting on the Cessna 421 at Reed Hillview that has had numerous panels with yellowing and paint degradation. It looks awfully similar to one of the PAFI candidate fuels from 2018. The yellow color of paint staining on aircraft that have utilized G100UL appears to be tied to a component called M-toluidine. But what's in the Shell fuel? It contains between 2% and 10% of aniline, which is another aromatic amine. It acts as a good octane booster, yet also yellows with exposure to light and air. So putting this all together, I'm theorizing that the center photo here is actually from Shell's candidate fuel in 2018, which had an aromatic amine called aniline. And the Cessna 421 at Reed Hillview has had similar yellowing and paint damage due to an aromatic amine. So I think it would be wise to heed the advice and wisdom from the fuel development and testing lessons learned from the PAFI program. One of the other fascinating reads in this fuel endeavor is a book from the Ethyl Corporation, which is titled Aviation Fuels and Their Effects on Engine Performance. As always with wartime efforts, the government spends a significant amount of money and there's a lot of research done in short time frames. And I think we all can benefit from what was learned with fuels back in the 1950s. This book goes into many of the chemicals that were tested in wartime engine development, including aniline and aromatic amines. But more importantly, it talks about the effects of fuel on rubber, and how many of these chemicals are solvents, and they're powerful ones, at minimum. It talks about the solvent effects of fuels on rubber systems, which was either significant swelling or disintegration. There's also mention about alternating between low and high aromatic fuels and the effects that has on rubber, and that it actually might remove some of the plasticizer and shrink the component. I've referenced Parker's O-ring handbook previously, and it discusses the effect of a fluid on the O-ring material, noting that the plasticizer or components of the compound can be extracted or leached out by the media when it's absorbed in a fluid. I mention this because one of my theories, especially in the PA32, is that when alternating between different types of fuel, i.e. G100UL or 100 low lead, the owner of that aircraft has had leaks in the fuel sender gaskets. And any chemical reaction by the elastomer absorbing the medium can result in a degrade in the physical properties such as embrittlement. And here it cautions about shrinkage due to plasticizer extraction causing seals to shrink. And it's certainly a consideration that needs to be looked at for long-term usage of fuels. As noted earlier, especially in the PA32 case and rubber gaskets, I think this may be one of the things that we're seeing in materials compatibility in the field. And don't get me wrong here, the development of a high-octane avgas is an extremely tough problem that many smart and talented chemists and engineers at major oil companies have worked on over the years. G100UL's fuel rollout hasn't been hiccup-free, and it appears that other companies may have learned these same lessons and opted to not go down similar paths. I highly encourage individuals to take a look at the documents in the PAFI program regarding lessons learned and development practices that were released based on previous candidate fuels. The FAA recently issued guidance on grant assurances in relation to 100 low lead and whether an airport sponsor may prevent or discontinue the sale of 100 low lead. It was stated clearly that an airport sponsor may not take action or fail to take action that would directly or indirectly prohibit or restrict access by airport users to 100 low lead. It was also noted that no unleaded fuel currently meets the criteria in Section 770 and is authorized for all aircraft. A few thoughts as I close out here. Individuals are obviously going to have to weigh the pros and cons of each fuel in their situation. It appears that materials compatibility issues are now being acknowledged by GAMI by way of their STC disclaimer. Materials replacement and mechanic privileges have to be carefully considered. It is unclear at this time what exact impacts will be levied with the use of other unleaded fuels for higher performance engines when they come to market. Some might say the sky is falling with 100 low lead sunsetting, but I'm confident we'll have a workable solution that balances materials compatibility and engine performance. And some personal long-term thoughts. Based on the material compatibility issues, I'm personally coming to terms with the fact that a long-term solution may be adjustments to our aircraft and engines, along with the development and implementation of new engine technologies. Don't get me wrong, I really like my current aircraft. I know people who fly older warbirds, but they are based on legacy designs, and we all know there are many barriers to development and certification of new engines, namely money. But I think for the GA fleet, there's definitely a need to use more modern technology that may not require a high octane fuel. As always, thanks for watching and have a great day.